break, like we looked at the idea of hyperparameter, right? Like so whenever you have hyperparameters, these are typically not trained or like this is typically not found through the training data, right? Like so, like we want to find a good hyperparameter by using a separate set, right? Like which led us to create the validation set, right? So now, given any data set, we want to split it into train, validation, and test. Now let's talk about more practical things. Like so, let's say I give you a data set. What is a good strategy to do this split? So how would you split the data into train, valid, and test? I think it matters a lot. Okay, so if you do random splits, you could get into issues that you did not think about. So think about it. Like so, I would like to get some suggestions on how to split the data into train, valid, and yeah. So you want to make sure that the distribution of features are same across all the three sets. Okay, that is a good requirement. Any other thoughts? Yeah. Okay. So you don't want to pick consecutive data. Now this, okay, I think a bunch of people walked in. So for people who are just coming in, like, so we are talking about how to split the training data into train, valid, and test, right? So what is a good strategy to split your data? Okay, so your suggestion, the first suggestion was to make sure that like your distribution of data in all the three sets is similar, right? The second suggestion was not to pick the data consecutively, like pick it in a different way, right? But this is assuming that the data comes consecutive. So if I already give you shuffle data, then it doesn't matter, right? Yeah. Okay, so just in case, it's a good strategy to shuffle the data and then split. Okay, you're talking about 70, 80. So what is a good percentage to split? Like, so like if I have a data set, what fraction of it should go to train? What fraction of it should go to validation? What fraction to test? Yeah, yeah. 60, 20, 20. So any other numbers? Yeah. Okay, 70, 15, 15. Anything else? Yeah. 70, 20, 10. 70, 20, 10. Okay. Well, I think the one trend I see here is all of you want to keep more data for training. Why? To learn the best parameter as possible. Like so, okay. First of all, there is no right answer here. Okay, so there is no gold standard that like you do 80, 10, 10 or 60, 20, 20, etc. Right? There's no gold standard. However, there are some guidelines. Like so, ideally, you want to keep as much data as possible for training, right? Like so, because that is where the actual learning is happening, right? At the same time, you don't want to have very little data for testing and validation, because then that is not going to be representative of generalization, right? So you need to make some balance here, like so keep as much as possible. I think 60 to 80 for training like is reasonable. So then you keep the rest for test and validation. Okay. However, if you have lots and lots of data, you could just do equal splits. That's okay, right? Like so we're talking about situations where you have enormous amount of data, which is often possible with the big data applications that we have nowadays, right? Like so if you have millions of data points, you can go ahead and like do 60, 20, 20, or like 50, 25, 25. So those things doesn't matter. Is that clear? So the split, you know roughly how to split, right? Like so, but in terms of the requirements for the split, I think one solid requirement is make sure that the distribution looks similar. Because if you put a bunch of things in training and your test set totally doesn't look like the training set, right? So then we cannot expect to see generalization. Is that clear? So in general, you need to think about all these things when you're doing the split. But in academic setting, especially in your assignments, we will work with standard data sets. These standard data sets come with their own splits. Okay, so you don't need to think about how to split. So like standard machine learning benchmarks, for sure comes with train and test. Most often comes with train, validate, and test. If it doesn't come with validation, if they just give you train and test, which is very common in computer vision applications, by the way, it's bad practice. However, like if it just comes with train and test, don't tune your hyperparameters with the test set. Okay, so you should create your own validation set out of the training sets. Like maybe keep 20% of the training set for validation, and do training with do the training with the rest of the things. Okay. Now, even with this setup, even if you are very careful, like in making sure that the distributions are looking okay, etc., right? Sorry. So you could end up in a situation where you were just not lucky. The validation set has some abnormal data points. So all you need is just one bad data point to increase the error significantly. Okay, so like you have a few abnormal data points in your validation set, and now that is going to wrongly guide you for like what lambda to pick, right? So how can I avoid this problem? Like, so how can I avoid the situations where I just picked a wrong validation set? What can we do? Yeah. You just repeat this several times. Like, so you repeat the sampling process several times so that if one of that is bad because you're not lucky, on an average, you get a reasonable performance, right? So this is the idea behind what people commonly call as k-fold cross-validation. Okay, so what is k-fold cross-validation? Like I'm going to take my training set. So here I'm assuming that there's a separate test set, okay? So we are not going to touch the test set, okay? So someone has given you just the training and test set. Now it is your job to come up with the validation set, okay? Now, just to make sure that we don't get into a bad validation set, so what we are going to do is we are going to split the training set into, let's say, 5 equal parts. In this case, we are doing 5-fold cross-validation, okay? I'm going to split it into 5 equal parts. Now, I'm going to run my experiment 5 times. Every time, I'm going to use one of them as the validation set. Okay? So the first experiment, I'm going to treat the first thing as validation and the rest as train. Okay? I get some validation performance. Then I'm going to use the second part as validation and the rest as train. I'm going to get some performance, right? I'm going to repeat this process 5 times. I'll get 5 validation errors, right? I'm going to take an average of all these 5 validation errors. So that is a reasonable validation error for the lambda I picked. Is that clear? Now you repeat this process for every lambda, pick the best lambda based on this average validation error. It's a very intensive process, okay? Yeah. Why? This is still validation set. You're not, this is still validation set, right? Like, so like you're not looking at the test set.
The thing is to be trained in one K times on the training set.
Oh, but these are K different models. right?
Not the same
No. These are k different. That's why I said these are 5 different experiments. Like so, so each time you're training a fresh model. Is that clear? But this process is just to find the best lambda. Okay. So now here is a practical question. So let's say I picked the best lambda. Now for each lambda, I trained 5 different models, right? So what would be my final model? Like so, what? Like I need one model in the end, right? Like so, outcome of model selection is one model. So let's say I pick a lambda. Now I have trained 5 different models for this lambda. Which model to pick? Yeah. You get into the same problem of lucky, unlucky validation sets, right? So what can we do? What can we do? Well, there is no right answer here. Okay, for a lot of these practical questions, there is no right answer. Okay, so what people typically do is once you figure out the best lambda, use all the 5 parts together to train a new model. Okay, then you get one model. However, there's a caveat here. Like the caveat is this is not how you selected lambda. So you selected lambda based on 4 out of 5 parts, right? Now you're training with all the 5 parts. So it is not clear anymore whether this is the best lambda. However, it's a reasonable heuristic and everybody does that. Is that clear? Yeah? Sorry, what? Yes. No, it's not the same validation. So for the second, you're using the second part as the validation. So now the first goes into the training set. Okay. Okay. So now I think we have covered almost all the basic components of a machine learning pipeline. Okay. So roughly, this is how any machine learning project is going to look like. Okay. So the first task is to define the input and output for the problem. Like, what is my X? What is my W? In housing price prediction, the X was the size of the house, Y was the price, right? So this you should have a clear idea. You should have a clear idea of what are all the features that is going to my X vector, what is my target, right? Like, is my target a real value or categorical, right? Like, you should have this information first. The second step is to collect examples for the task. Okay, so once you have identified X and Y, you're going to go collect examples. Okay, so once you have the examples, then you're going to divide the examples, okay, into train, validation, and test set. Is that clear? So once you have this split, typically you will do some sort of data pre-processing. So you will do some data pre-processing. So what do I mean by that? For example, it might be the case that some features are missing, right? So then how do I fill these missing features? So what would you do if a particular feature is missing? Like for an example, you have a data matrix, right? Some entries in the matrix are missing. Yeah. Well, if you start dropping every example which has missing value, you might drop a significant amount of examples. Every data point is valuable, right? Like, you don't want to drop them unless it's absolutely necessary. Yeah.
We can replace it.
Yeah, it's a number, right? Like, so often these features are numbers. So you could just take an average of that feature and treat that as this number. That's a, you can do mean, you can do mode. okay, or median. Like, so these are some heuristics, okay. So you'll do some sort of pre-processing, okay. So once you finish the pre-processing, so then the next step is you will define your model. You're going to say, oh, I'm going to use a simple linear model, or I'm going to use a polynomial regression model, right? You define your model. Now, when you define your model, the model is going to come with a set of parameters to learn from the data and also hyperparameters. Okay? Then the next step is to define the error function. Is that clear? So once you fix the error function, then the next step is you have everything now, right? Like, so then you do model selection, which means trying different hyperparameters, looking at the validation performance, either using k-fold or just normal train validation split, right? You do the model selection. So finally, you test the model with the test. Is that clear? Any questions so far? So, yeah. Okay. I was anyway about to ask this question. So I'm doing the data pre-processing after I split the data. Why is, and my argument is this is the right way to do it. Like, so what you're saying is not the right way to do it. Like, your suggestion is to do pre-processing before splitting, right? So why is it a bad idea to do the pre-processing before splitting the data? Yeah. And why is that a problem? Yeah. So you're kind of doing test data leakage by doing this. So if you do your data pre-processing before splitting the data, when you take an average feature, you're averaging over the test sets as well. So which means indirectly you're giving some information about the test set to the model. Okay. So this is the most common mistake that even experienced machine learning researchers would do. Okay. So you have to be careful in doing the pre-processing only after you split the data. So, like for example, there are some pre-processing where they look at the minimum and maximum of the value and do standardization or normalization of the features. Okay. Now, these min-max values you should take only from the training set. You should not include the test set. Then the model knows what is the min and max in the test set. Right? Ideally, you don't want to give any information about the test sets to the model. Is that clear? Okay. So this pipeline, right? Like, so it's end to end in the sense it starts from the problem definition and it goes all the ways to testing the model. Okay. I think this is the right time to tell you what exactly the focus of this course is going to be. Okay. We are not going to focus on every single aspect of this pipeline. Okay. So some of these we would assume that it is given to us. For example, the input and out, like the problem definition, right? We will assume that somebody is giving us a problem and we are just trying to solve it, right? So this course is going to focus more on the modeling side. Okay, so the data collection, we are not going to look at it. So this are dividing the data pre-processing, right? So most of this part, right? So it's going to happen from the data side, and this is often the focus of like a data mining course. So or a data science course. Okay, if you take a data science course, it's going to focus more on how to pre-process the data, like how to split the data, like so what is the best way to collect the data, like what is the best way to store the data, etc. Okay, so we're not going to look at that in this course. Like, so our focus is going to be mostly on how to define your model and what kind of models we could actually work with, right? And what kind of error function we could use, like so what kind of model selection we will do. I think we will talk a bit about evaluation, but we are not going to focus too much on evaluation in this course. Okay. I think, well, we have a new prof at GHL. Matt, who is teaching a machine learning evaluation course, uh, which could be a good course if you want to think about evaluation. Okay, evaluation is a very hard problem. It's not an easy problem. Like so, and especially if you want to deploy these systems, you should think carefully about how you evaluate. There are many practical examples where companies deployed a model with poor evaluation and just brought down their stock prices because the model was so bad and customers were not happy, right? ML evaluation is important, but we're not going to focus too much on that. Like, so our focus is going to be mostly on the modeling side, which is more algorithmic, and we will explore different kinds of models that we could use. We will explore different kinds of error functions that we could deal with. We will explore different ways in which you could minimize the error function or find the best hyperparameters, etc. Is that clear? Yeah.
The more problem is still learns from the tests. Well, it's still learning from it. That's the objects that are.
No. Why do you think model is learning from the test set? No, the model is not supposed to learn from the test set. You will just use the model to predict what the test set. You're not learning from test set.
Yeah, but after one just prediction and review the test set probably, but it's still update.
No. We typically don't update during that time. Okay. So there is another practical advice here, like which I think again something that even experienced machine learning researchers fail to notice, which is even though this process is set up in such a way that you never learn from the test set, this is not a foolproof process. Okay. So let's say you as a machine learning engineer is trying to come up with a solution like where you try one model, you do the whole process, you're not happy, you go back and change the model, or you go back and change the error function, and you repeat this process. Okay. Now you're indirectly leaking the test set to the model through your own personal biases, right? Like so, like because when you finish this pipeline once, you have already seen the test performance, and you're not happy, and you're going back to change the model, right? Which means you're giving some feedback to the system that, oh, this is not a good model for this test set, right? So you have to be careful. You as a person have to be careful when you're going through this pipeline again and again. Okay. So typically, you don't want to do this 8th step 100 times. Okay. So you want to do this as little time as possible. So in more complicated practical pipelines, people would have multiple test sets. Okay. So you can have, just like how we have train, validation, and test, you could have val1, val2, val3, and test, like where you're using val2 once a while, and then like you use val3 once a while, right? So there are more complicated ways to avoid this problem, but this happens all the time. Like if you iterate too many times, you are essentially seeing the time. So you should know this, like so you're making your judgments. Is that clear? Any questions? Okay, I think we touched a lot of things today. So now let us go back to the polynomial regression. We're going to do a bit of modeling. So our polynomial regression equation looks something like this, right? Like so y hat of x given w is equal to w0 plus w1x plus w2x square all the way to wm x over m, right? So I told you that this is still linear model, right? So typically, when you have a linear model, okay, you give some x and you get some y. This model is often like it's always going to give you some linear function, right? However, with polynomial regression, I was able to get nonlinear functions because with different degrees, you can get more complex functions, right? So if you think carefully, like what we did here, so it was almost a hack. So we took a linear model, which was linear regression, right? So this is a linear. If you just feed X and do linear regression, you're going to get only a line, right? Now, instead of feeding the X directly to linear regression, what we did is we created a bunch of nonlinear features, X square, X cube, etc. Right? So what we did is we took X and we created some nonlinear features. We're going to give a name for these features. Okay, so these features are called nonlinear basis functions. Okay. Then I was feeding these nonlinear basis functions to the usual linear regression model, which gave me some Y. Now this whole thing actually became a nonlinear function. Okay. There is another way to get a nonlinear function, which is simply take X, instead of using a linear model, just use a nonlinear model. This is also going to give, these are two different ways to get nonlinear functions. Okay. Now, why did I pick this route instead of this route? It's easier. Why is it easier? It's kind of easier because with the linear model, we know the closed form solution, right? So by just adding nonlinear basis functions, like so, we were still exploiting all the benefits of the linear model while also getting the benefits of nonlinearity. Okay, so in some sense, it's a hack. This is not a nonlinear model. Like so, like we made it nonlinear by using a bunch of features, right? Like a more general family of nonlinear models would look something like you'll just take X as input and do some nonlinear computation and give Y. Okay. However, those are kind of difficult to train models. Okay, we're going to talk about nonlinear models like in the future. It's just much easier to train the first class of models than the second class of models. Okay, so for now we are going to exploit this fact that I can create nonlinear features and still use linear models, and I'm going to get nonlinear functions out of it. Okay, now I can actually generalize this idea. So here are the general class of linear models with nonlinear basis functions. Okay, so y hat of x given w is given by w0 plus w1. I don't need to do always x square x cube. I can do any nonlinear function that I want. So let's just call it phi1 of x. So phi1 of x is my first nonlinear feature. Okay, it could be x square, could be e power x. Like you can do whatever feature you want. Plus w2 phi2 of x plus all the way to wm pm of x, where pj of x is my basis function. Okay, these are usually fixed non-linear functions. Okay, so if I have to write this in a compact notation, then y hat of x given w is equal to summation j is equal to 0 to m wj pj of x. Okay, or simply w transpose phi of x. Phi of x is a vector. Okay. So here w is my parameter vector, w0, w1, all the way to wm transpose, and phi is my feature vector. So phi0, phi1, all the way to, yeah. Is that clear? So I have just generalized the idea of polynomial regression to any type of nonlinear basis function regression. Okay. So now polynomial regression is just a special case, right? So if I have to write I'm going to write some examples for basis function. The first example is something that we have already seen, which is polynomial basis function. So the polynomial basis function, phi j of x is simply x power j. If you just put phi j of x to be x power j, you're going to get the polynomial function, right? Now you can use other fancy basis functions. Like for example, you could use Gaussian basis function. Okay, the Gaussian basis function is going to look something like this. So phi j of x is going to be exp of minus x minus mu j the whole square by 2s square, where mu j and s, right? So these are hyperparameters of this basis function. Like you will pick a bunch of mu j and x. Like mu j basically governs the location of the basis function, and s is basically the spatial scale. It looks like a Gaussian. It's not exactly a Gaussian. Okay, that's why it's called Gaussian basis function. Okay. Now you can also have sigmoidal basis function. Sigmoidal basis function, like which is going to be phi j of x is simply sigma of x minus mu j by s, where the sigma function, sigma of a is given by 1 by 1 plus e power minus a. It looks something like this. Okay. You could have really simple identity basis function, which is phi of x is equal to just x, in which case there is no basis function. You get simple linear regression. Is that clear? So now different basis functions would look something like this. Okay. You see the polynomial basis function, depending on the degree, is going to look like different polynomials. Gaussian basis function looks like Gaussians, and the location of these Gaussians is determined by the mu j and s. The sigmoidal basis function looks like sigmoid, and the location is again determined by mu j and s. Is that clear? So typically what we would do is, given a data set, let's say we want to do Gaussian basis function, we're going to pick 10 random values for mu j's and s and construct 10 random Gaussian features and project the data to these features and then do linear regression on top of it. It looks chaotic, but the nice thing is when you mix a bunch of these Gaussians together, you're going to get a really complex function. Is that clear? So the nice thing here again is the solution doesn't change. The solution is always the same, okay? The solution for polynomial, sorry, Gaussian basis function, like any basis function regression, is still P transpose P inverse P transpose Y. I'm using phi instead of x because we are using nonlinear features. The solution is still same. Is that clear? Any questions? Okay, so I want to talk about one last thing before we conclude, which is so far we have been doing regression where the output is just a single scalar, right? So what if my output y is a vector? So what if my output y is a vector? Do I need to change the whole setup? So again, this is one of the benefits of switching to the matrix notation, okay? Because we are doing everything in the matrix notation, the solution is going to work out of the box even when y is a vector, okay? So when y is a vector, my x is going to be a data matrix, right? The x is the data matrix which has n cross p elements, right? My y, which used to be a target vector, is simply now a target matrix. So let's say my output has 10 values that I'm predicting, okay? And this is simply n times 10. Is that clear? Now, if we go back to the solution, right? The solution was, oh, now my W is going to be a matrix, not a vector. Okay, my W star is going to be phi transpose phi inverse phi transpose Y. Now, because this is a matrix, this is also going to be a matrix. Okay, so if you have 10 outputs, then W is going to be a matrix of size, the number of features times 10. So I know I'm saying this very quickly, but I want you to go back and think about it. Okay, so think about how you can adapt the linear regression solution when y is a vector instead of a scalar. Okay, so my point here is nothing changes. Like, so you still get the same solution. Yeah.
You treated for
Yes. So you will have features. Well, no, W is a parameter, right? You have these are parameters. X, P is the feature, Y is the target.
yeah, so I guess it's a comparative, feature of
No, you're not predicting features. You are still predicting the target. Okay. Any questions? Okay. So yeah. Okay. So the size of the Y, if your output is a 10-dimensional vector, then Y is n prime 10. Okay. So okay. So X is sorry. Okay, that's a lot of slides. Yeah. So your X is n cross P, Y is n cross 10. Can someone tell me what would be the size of the W matrix? P cross 10. Okay. Because you'll have a P vector for all the 10 outputs. So it's P cross 10. Okay. Okay. So I think we will stop here. This week, we looked at simple linear regression with different flavors of polynomial regression, etc. And we were still able to compute closed form solution, right? Like, so the next week, we will talk about what can we do when we cannot find closed form. Okay. But before that, remember that assignment 1 will be released today. You should start working on it from today. You want to finish it today. And this is my office hours. If you want to talk to me, just walk with me.